So what we're going to do now is we're going to put together some ideas that we've learned throughout the course, and we're going to use those ideas to think about a very important example of a molecular communication system, and that system is known as signal transduction. So to be more precise, what we're talking about here is a family of molecular communication systems, and these are communication systems that allow intercellular communication, where the signal-bearing molecules are called ligands. So this is molecular communication in the original meaning of the word, and it uses all of the assumptions that we've talked about so far. So basically the setup we have is this. We have a transmitter cell. The transmitter emits molecules. These are the ligands. The ligands will propagate via Brownian motion. And at the receiver will absorb these. So the receiver in this case is absorbing. And it has on its surface a number of very specialized proteins called receptors. And the idea is that a ligand propagating by Brownian motion will randomly encounter a receptor and bind to it. That action in which the ligand binds to the receptor sets off a cascade of chemical reactions across the cell membrane and produces what are called second messengers. That cause the receiver cell to take some sort of action. So the meaning of these signals isn't terribly important to us. What we're going to analyze is how this communication channel works, and you can already see that it fits nicely within our framework. We have this transmitter that presumably either generates or has a reservoir of ligands, releases those ligands. We have Brownian motion, and then we have the molecules encounter the receiver. So this is obviously a communication system, and the question is, how exactly do we analyze it? So while this communication system has many features that we've discussed, the twist right now, the twist that we're going to add is that the chemical reactions that occur at the receptors, we're going to directly model those. So we're going to bring together this idea of Brownian motion, communication, and, Brownian motion, creating a signal that's transmitted across the channel, and biochemical reactions like we talked about in the very beginning of the course. So signal transduction can be accomplished by proteins that undergo chemical reactions. So here we will model those reactions directly. And before you get too afraid of what's going to come next, it's actually not complicated at all. We've already developed the machinery we need to analyze these in a discrete time, actually in both discrete and continuous time, but if you like working in discrete time, this will turn out to be just a Markov chain. So that's where we're going. In order to get there, we're going to consider a specific example. And that specific example we're going to consider is the cyclic AMP receptor. The cyclic AMP receptor is famous as a model system for analyzing signal transduction. It has a very important role in what are called slime molds. Its action is very well known. Basically, what happens is these slime molds grow in a medium with food. Then they start to notice that the food is dissipating, so they're about to starve. And what these organisms do is they send cyclic AMP signals to each other that basically tells them to prepare themselves for famine. And then what they end up doing is they end up growing what's called a fruiting body and creating a spore that will survive the famine and will wait for more food to come along. So the reason why cyclic AMP is in particular widely studied is because it's very simple. So we can model this. By the way, we abbreviate this as little lowercase c AMP. We can model as a two-state finite state machine. The two states are called bound, or B, and unbound, or U. So what's going on in the bound state, that's where your receptor has a ligand. So a ligand of CAMP is attached to the receptor, and it's producing second messengers. In the unbound state, that's where the receptor is quiescent. So it's just sitting there waiting for a ligand to arrive and not doing anything. The key thing to note here is that both states require some processing time. So we're going to see that in a second. Basically, what we end up with is there are two simultaneous reactions. We have, this can be modeled as a forward and a backward reaction, two simultaneous reactions. So if you have an unbound ligand and you react it with a molecule CAMP, it will produce a bound ligand. And the reverse is also true. So you don't get back, it's convenient, it'll be convenient to call this the reverse reaction. You don't necessarily get back the CAMP, but you do definitely get back the unbound receptor. And so basically it'll, since all you're really concerned about, the CAMP concentration is assumed to be constant, all you're really concerned about is the proportion of U and B. We could also write this as follows. U reacts into B, and B reacts back into U. Now, think back to an earlier lecture when we were talking about these kinds of chemical reactions. Each chemical reaction will have a rate. So I'm going to call the forward reaction here K plus from unbound to bound, and I'm going to call the reverse reaction K minus. And remember, we can write down a master equation. We'll get to that in a second. But what I also want you to notice is that by the principle of mass action kinetics, which we also talked about, this forward rate, so if it's posed in this way, this forward rate from U to B is dependent on both the concentration of U and the concentration of CAMP. So I'm going to write this notation. That means the concentration of CAMP. So if you had square brackets around a chemical species, that means its concentration. Okay, so what we see, again, principle of mass action kinetics, the forward reaction is a function, is proportional to the concentration of CAMP, but the backward reaction is not. So the backward reaction is only dependent on the number of B. We'll assume that's constant. So the reverse reaction rate here is a constant. So this lets us set up a master equation. So we're going to do it this way. We're going to say just give me a moment to make sure I'm getting this right. Right, so basically, to set up this as a master equation, we would have to do something like this. D by dt, concentration of U, concentration of B is equal to the rate matrix, which is going to be from U to B, I have K plus, so I have minus K plus, and again, I combine that with the concentration of AMP. And again, the columns sum to 0. So that here I have from U to B, and then from B to U, I have K minus. Multiply that on the right by again, those same concentrations. So we derived, or we went through kind of a hand-wavy explanation of how the master equation worked in an earlier lecture. So this should not come as a surprise to you. It's just that we've identified a specific system with specific concentrations. Now, I want you to look here. What is this? So here we have the concentrations of U and B. So I could just as easily call those the numbers of U and B. So I could call this NU and NB. And they are equivalent up to a constant of proportionality. Basically, I divide by the total number of molecules. So I can certainly call those the numbers of U and B. So again, I could have the rest of it over here, and that's still number of U and B over here. I can take that a step further, and I can ask, I can actually multiply that by, or take out another constant of proportionality. And I could say this, I could say number of U divided by NU plus NB, number of B divided by NU plus NB, times NU plus NB is equal to, again, my rate matrix there, R. Let me actually write the rate matrix there. That's what I meant. So this is the rate matrix. In fact, let me clean that up a little. Coming back over here. Again, there's no difference if I take out that constant of proportionality over here. Like so. Now, what is this? This is the probability of if I pick any given receptor, this is the probability that it's in state U and the probability that it's in state B. So now I have a master equation in terms of probability. Now, these constants of proportionality don't matter. I can divide them out on both sides. And I'm left with this. So d by dt, sorry, that should be d by dt over here. is equal to PU PB is equal to R PU PB. So now we have a master equation stated in terms of probability. We can take this a step further. And what I'm interested in now is I'm interested in discretizing this. I'm interested in turning this into a discrete time system, because what you'll see is that it is in fact a Markov chain. And how it works is that if I take that dt across, so basically I have this dp is equal to r p dt. But dp over very short timescales, that's p at t plus delta t minus p of delta t. Excuse me, sorry, that's not right. That's p of t is equal to rp delta t. Again, that's p at time t delta t. So I can write this as p of t plus delta t. Take this guy across, p of t plus r p of t delta t. Rearrange on the right-hand side a little bit. What I can do is I can take out an identity matrix. So if I multiply, this is a column vector. P of t is a column vector. If I multiply on the left by the identity matrix, it does not matter. And then I'm going to collect r and delta t here. Delta t is a scalar, so it doesn't matter when I multiply it. And I can then take pt out here. And I get I plus r delta t, p of t. And that is p of t plus delta t. So think about how this worked. What's going on now? This is the state occupancy probabilities. After one time step. These are the probabilities originally, which makes this, so this is just one step of a Markov chain. If I have a vector of probabilities of being in each state, and I'm interested in what's the vector of those probabilities at the next time instant, I just multiply by this, which is the transition probability matrix. So that is very nice. What we've done is we've started with our chemical master equation, which we talked about. We know how this works. This is mass action kinetics. This right here is just straight physics. In fact, we start with our chemical reaction. We write the master equation. Then just by simple manipulation, actually coming back here, we can convert by taking out a constant, like the number of total molecules. We can convert this into numbers of receptors in the unbound and bound states. It works the same because it's the same constant on both sides. And I can take out another constant, the total number of receptors, and I get these, I get these fractions. And those fractions, if I pick one receptor at random, that is the probability of finding any particular receptor in those states. So I have a rate matrix. This is now a continuous master equation in terms of probability, and it becomes a finite state Markov chain. So this equation gives the finite state Markov chain. For any R. So that's really nice. We know very easily how to simulate, how to analyze, and how to deal with finite state Markov chains. Basically, what we've done is we have taken a seemingly very complicated biochemical reaction system, and we have converted it into a mathematical object that is relatively easy to deal with. So in other words, you could even restate this as follows. So the system in discrete time we have probability at interval k is equal to, I'm going to call it Q, pk minus 1, where Q is the transition probability matrix. Q is I plus R delta T. Just a couple more comments about this. You'll remember that the steady state probabilities are given by the zero eigenvalue. The eigenvalue corresponding to the eigenvector corresponding to the zero eigenvalue for R, and R always has a zero eigenvalue. If I multiply by delta T, it doesn't change the fact that it is zero eigenvalue. If I add the identity matrix, then all of the eigenvalues increase by 1. So now I'm looking for the unit eigenvalue, and the corresponding eigenvector is the steady state solution, which is a well-known property that we know of Markov chains. So everything is consistent. That's really nice. Now, the final issue that I want to leave you with in this part of the lecture is, how do you use this to communicate? And the real issue is that we know that the transition rates, some of them anyway, are sensitive to concentration. So this seems like a job for concentration shift keying, and that's exactly what you do. So the chemical reaction we're looking at here, remember, it looks like this, where this forward reaction is a function of the concentration of CAMP. The backwards concentration is not. So if you think about what's going on, suppose the concentration is very low. The concentration of CAMP is very low. Then if we start in state U, this forward rate is very small because CAMP is very low. This forward rate is very small, meaning we spend a lot of time in state U. So we wait a long time, and then eventually we'll go to state B, and we come back at whatever rate. Spend a lot of time in state U, go to state B, and come back at whatever rate. And it seems like we're going to spend a lot of time in state U. On the other hand, if if the concentration of CAMP is very high, then we don't spend a whole lot of time in state U. If we start in U, we go very quickly to B, come back at whatever rate, very quickly to B, come back at whatever rate, and so on. So what we can see is that we're using a CSK-like modulation scheme at low concentration. We spend a lot of time in state U. At high concentration, we spend a lot of time in state B. In fact, you can be analytical about it. You can actually determine for a given CAMP concentration, you can determine the probability of being in U and B by solving this matrix for its unit eigenvalue and the associated eigenvector. And that gives you the probability of being in both U and B for a given concentration of CAMP. So for low concentrations, you'll see a certain set of probabilities. High concentrations, you'll see a different one. And basically what you can do is you can say, at low concentration, I'll look at a receptor and see what probability it is of being either U or B, and perhaps that's a 0. If you detect a 0, maybe a U, maybe you detect a 0, and vice versa. If it's bound, then maybe you'll detect a 1 at high CAMP concentration. This is just an example of a way in which you could design a modulation scheme for CAMP using a signal transduction system. There are many, many, many complexities to this, but this is the basic idea. What you're going to do is you're going to get R. You can get R, the kinetic rates for a variety of receptors in the literature. They're published in papers. You can solve. You can draw out the chemical reaction network. You can solve these things. One complexity is that not all of these states are necessarily observable. Some of them are hidden, which leads you to talking about hidden Markov chains. But there's many interesting ways in which you can study these kinds of systems, and I will leave it to you to take it the rest of the way.